This is going to be the video for Chem 102. This is going to be sections 14.7 and 14.8. So we're going to start with reaction mechanisms today. And a reaction mechanism is basically explaining the steps that a reaction takes, because sometimes reactions don't just happen all at one step. So often we may just think about like, oh, this is going to come apart and this is going to be put together. But it's not just happening instantaneously in that one step. Sometimes there are byproducts, sometimes that are intermediates, like things that you make in between step one and step two. If you think about cooking, sometimes you can imagine that this happens. Like sometimes when you're baking or cooking, you have to make something in between steps that doesn't actually seem like it's part of your final product because it goes into the next step and gets used up. Um, and that would be like something called an intermediate, which we'll talk about in a moment. So the sequence of steps that we see would be the reaction mechanism. Oh, and the slide is missing step one here, so let me try to fill in what step one would be. Step one would be A plus B makes C. So for this generic reaction, first step is A adds B to make C. But then the second step, we take C and we use it. So C actually cancels out in the overall reaction. So my overall reaction, thinking about Hess's law, kind of adding things up, it's A to B makes D. So that'd be an example of a reaction mechanism. If you see that you're making something and then using it and then in a later step, it's called an intermediate. So an intermediate is something that is created as a product. So we see it on the right side first, and then used as a reactant. So we see it on the left side next. So in a later step, we're using it up, and it cancels out. It's not going to be in the overall reaction because it cancels out. Just like in Hess's law, we saw this kind of happen where we had these things and we canceled out. We were actually looking at like different steps of reactions. We just weren't calling them mechanisms. And here we talk about mechanisms because we want to talk about rates. Hess's law more is about thermodynamics, or how does it happen, and these reaction rate mechanisms are more about how fast does it happen. So each step in a mechanism is called an elementary reaction. So it's a single collision. And so we have different types of elementary reactions when we describe them by their molecularity. So molecularity, an elementary reaction. Molecularity is the number of reactant molecules that are involved in the collision. So if it's unimolecular, uni meaning one, like a unicycle, uh, there's only one reactant molecule, and it's just that one molecule breaking apart, for example, because you can't have, if you have two of the same molecule, that's still bimolecular, but one molecule making a product. So essentially you would think about it as like one molecule breaking apart to make a product. Bimolecular is two, like a bicycle. And this is very common. You'll see what we normally kind of think of is like, hey, we'll have two reactants hit each other in the right place, and then that will make our products. You can have two different reactions. Like in this first one, it's A and B, and then you could have two of the same reactant, like A is colliding with another molecule of A. The overall order for a bimolecular step is second order, and the overall order for a unimolecular step is first order. Notice that this one is second order because the overall order is 1 plus 1 here. So it's not that both of the reactants are second order. And then it's way less common, but you can have termolecular. not tri. I know you would think it would maybe tri here with the trend, but it's ter, and that would be 3 reactant molecules. So the higher the molecularity, equals harder to get effective collisions. So think about it. If I don't have to collide with anybody else, I'm just going to break apart. That's really easy, right? If I have to collide with someone else, even if it's a molecule of the same substance, I still have to collide. I have to collide with enough energy. I have to collide at the right orientation with one other thing. If there are 3 things, then 3 things have to collide at the right energy, at the right orientation. So you can imagine that maybe you get a situation where 2 of the things are colliding with the right energy and orientation, but the third one's not. So it's like trying to get 3 people to come to a consensus and like work together versus 2 people versus 1 person, right? So that's the harder, the higher up you go with the molecularity, the more collisions you have that are involved, more molecules that are involved in the collision, the more difficult it is to get an effective collision. So in a rate determining mechanism, or a rate mechanism has more than one elementary step, the rate law for the overall reaction, so the rate law for the overall reaction, the like reaction you're looking for, is given by the rate determining step. And the rate determining step is going to be the slowest step in the process. And so the mechanism has to satisfy 2 requirements in order to be a viable mechanism. First, the sum of all the elementary reactions have to be the overall balanced reaction, and the rate determining step has to have the same rate law as determined from experimental data. So it has to match experimental data with the rate determining step matching the experimental data. So if the rate determining step says A is second order, but the experimental data says A is first order, that doesn't match, right? So that would not be a good mechanism. We would say, hey, that mechanism is flawed. And then if you added up the reactions, the elementary reactions, and you didn't get the overall reaction, like you did like the Hess's law stuff, like we're not talking about Hess's law and then like we can move them around. Like we are not allowed to move them around. But if I can't just look at it and add these up to get this one, then it's not a good mechanism. So we'll have to go back to the drawing board there. So here is an example of a mechanism. Hydrogen peroxide decomposes, and then it's facilitated by iodide ions. Iodide ions here are acting as a catalyst. We'll talk about catalysts a little bit later, but it's going in and kind of helping it out, and then it's leaving. So it's like kind of a matchmaker, right? It's going in, orienting things correctly, and then it's leaving. But it's not part of the overall reaction because you would cancel it out if you were adding them up. So if they tell me the step 1 is slow, step 2 would be faster. The overall reaction is the 2 of these added up. So let's think about what we can cancel. We can cancel out I minus. We can cancel out IO minus. And what are we left with? 2H2O2, 2H2O, and an O2. And so this mechanism works for rule number 1, which is we can add it up to get the overall reaction. Now let's check to see the rate. So the slow step, so the rate here we know is first order with respect to H2O2 and first order with respect to I minus, and that matches the slow step because they're both coefficients of 1. I might have to see what your textbook says because I have not been taught to use catalysts in rate laws. So I will have to check to see what. Okay, so we do your textbook is going to have them included. That's fine. Just some books will not include catalysts in rate laws. So if it is in the slow step, even if it's canceled out because it's a catalyst, it's going to be used up, it would be included. And so if you were just to look at this overall reaction, you would look at this and you would say, wait, I minus, and you might have a question there. So according to this mechanism, I minus is, it's part of the the reactants of the slow step, so it matters. What we do is we take the coefficients in front of the substances in the slow step, and those become your orders. But this is the only time in which we can make the coefficients the orders. It's when we're looking at the slow step in a rate mechanism. Okay. And then of course the rate constant is of this first step. So they'll say K1, right? Because it's the step that determines the rate of the reaction. So here's what a reaction diagram would look like. Start with our reactants, we have our products. We're gonna go have two humps. Each step is gonna represent a hump. So we have the activation energy for step 1, get to that transition state, and then we go down to the products of step 1 is the intermediate. So this is the products of step 1 is the reactants of step 2. And then we go to the activation energy for step 2, and then we go to make our products. Notice that the activation energy for step 1 is a lot higher. This is why it's the slow step, because it's got a higher activation energy. The higher your activation energy is, the slower you're going to go. Because it's going to take, if I'm walking up this mountain, it is going to take me a lot longer to walk up this hill. And if you started here, you would get to the top of your hill way before I would get to the top of mine, right? So this is the slow step because it's got a larger activation energy. And activation energy is always the top of your hill minus the reactants. And so if our step 2 reactants are here, the top of the hill minus the reactant, so this would be the activation energy. And notice that they're using this little mark here to indicate that it's the step 2 one. So we have the original and then the next one, which is step 2. You might see EA1 and EA2 as well in the textbook. So why don't we try answering a couple questions. So first, here is the mechanism. The rate law is found to be K into O. Write the equation for the overall reaction, tell me what the intermediate is, and identify the rate determining step. Okay, so if you paused and you tried it on your own, that's great. If not, try it, just guess. And then if you have already tried it, then let's talk about it. What's the equation for the overall reaction? So overall reaction, we have N2O and N2O. Let's see what we can cancel. We can cancel O and O. And then what are we left with here? We're left with 2N2O. And then 2N2 plus O2. Because we canceled out the O's. So that would be our overall reaction. What's the intermediate? Well, the thing we canceled out was the oxygen, right? So our intermediate is going to be a product in a previous step and a reactant in a later step. So that would be oxygen. And then what's the rate determining step? So if the rate is first order with respect to N2O, it could be, so you're thinking about, oh, these are both ones for N2O. However, step 2 has the oxygen in it. And so it's probably less likely to be the rate determining step because then the rate law would have to have oxygen in it. And we don't see the rate law with oxygen in it. So we'll say step 1 because 1 N2O and nothing else. So sometimes you have a fast first step and a slow second step, and that's all right. when we write the overall rate law using the equation, we see that in this one, we include the intermediate. So if the slow step is the second step and has the intermediate in it, it's going to be included in the rate law. And notice that these are both ones at their coefficients. That's why they're first order here. So when the intermediate is not consumed by step 2 as fast as it's produced in step 1, its concentration does build up, causing step 1 to happen in reverse. So if basically we get a backlog of this intermediate because you're making a lot of the NOCl2 and then you're not using it up because this one is slow. And so this causes an effect and it causes the reaction, the fast reaction to kind of go back and forth. So it's going to go in reverse because we got a buildup of NOCl2. We'll talk more about this process. It's called equilibrium, and we'll talk more about it in the next in a later chapter. But it does, if you increase something that is a product, it can shift a reaction kind of back towards the reactants. And so that's what's happening here. So a lot of times when we see we have a fast first step, this is the same slide, we would see it written like this with these back and forth arrows. So when we have those back and forth arrows, we have to analyze, okay, well, what is my rate law here? Because if I don't have to include my intermediate in my rate law, I don't want to, because it's confusing to look at the overall reaction and see something that's not actually there. With a catalyst, it makes a little bit of sense because I am going to be adding the catalyst at the beginning, but I'm not going to be just like adding the intermediate anywhere. So if we have this fast first step that's reversible, the reversible means that the rate forward and the rate reverse are the same. So if we think about what the rate law forward would be, like assume this is the slow step, what would the rate law be? The rate law forward would be 1 NO, 1 Cl, and we'll call it K1. Rate reverse, so imagine now this is my reactants. Rate reverse would be 1 NOCl, and the K would be -1. So we're saying in reverse. These two rates are equal to each other. So I can set this and this equal to each other, which is what we've done here. Then if I simplify and like combine my rate constants here, we'll call what are they doing here? So we can isolate the NOCl2. And so remember our previous, and we'll do this in class again. Remember our previous one was rate equals K2 NOCl NOCl NO. And where I see NOCl, NOCl2 is what I meant to write there, NOCl2. Where I see that, I could actually just plug in here. I could plug this in because this is what this whole thing is equal to NOCl concentration. So when we do that, we're going to plug this in. Let me just highlight again. We're going to take this and we're going to plug it in where it says NOCl2. And then we get this whole thing. Now we can just say, hey, let's just call this whole thing K3, for example. And so then my rate is some new constant, and all these K's are just constants, and so we could find what the actual constant is, the new one it is, because it would just be K2 times K1 divided by K -1. And then we would have NO, and then we had an NO originally, and we had a second NO, so that would be NO2, and then we have to add in this Cl2 from the others, this one. So again, we're going to do this in class, so it's a little bit easier. It looks really complicated, and it's not quite as complicated as it looks if you break it down into pieces. Why don't you try it? this should be a back and forth arrow. It's kind of, they have a hot mess over here. So this one is going to be back and forth. And it's fast. So it's fast and reversible. We're trying to figure out how this mechanism, if this mechanism matches, we got to figure out how to make this mechanism match this experimentally determined rate law. So give it a try to see if you can figure anything out, and if not, that's okay. This one's kind of tough. So if you see in our experimental rate law, we don't have any N2O2, but N2O2 is in my slow step. So, all right, let's look at the rate of the slow step. So rate of the slow step, rate is equal to, and they use K2 here, so I'll say K2 is equal to N2O2 N2O2 times O2. All right, well, that does not match this, right? So I have got to figure out how can I, work this out. Well, this is reversible. So let's look at this fast step. So we know the rate of the forward reaction is going to be NO times NO, which would be NO squared, and it would be K1. And we know the rate of the reverse reaction would be N2O2 raised to the 1 power, and then that would be K to the negative 1 there. So let me add that in. To the negative 1. And then when we have this equilibrium system, the system where we're going back and forth, the rate forward and the rate reverse are equal to each other. So we can say K1 NO2. Now the reason I'm putting a 2 here is because there are 2 of them. There's 1, there's 1. So if I put NO next to NO, that's just going to be NO squared. And then I can say that's equal to K negative 1 N2O2. Well, N2O2 is what I have that I don't want. So if I can solve this for N2O2, I can plug it in here. I can do a substitution. So let's divide both sides by K to the negative 1. And that will cancel this out. And that's going to give me N2O2 is equal to K1 over K negative 1 times NO squared. So then I can take this whole piece and plug it in where I see N2O2. So I can get a rate of K2, K1 over K negative 2. And these Ks are arbitrary as far as we're concerned because they're just numbers that we could find, right? And then instead of saying N2O2, we'll say NO squared, and then we'll say O2. Um, Something is wrong here. I think that they messed up because there's no N2O at all even in here. So there we go. It's supposed to be NO squared. That doesn't make sense. And so if we know that this all would just kind of devolve into, let's just call it K, then we're finally showing that our rate is equal to some K NO squared O2. And they had messed up there with a typo. But hopefully, now, so if the question says show it, right, what I've done is I've taken you through showing you, okay, well, here's the slow step one. I showed the rate forward, rate reverse. I put them equal to each other. I'm solving for the intermediate that I don't want to have in the rate expression, and then substituting it in, and that substitution is going to give me the thing that matches the experimentally determined rate law. And again, I believe that this is an error here, so we'll correct that. And then the new K is just, equal to the old K, so we'll just call it K. So how can we know if a reaction mechanism is correct? So we'll always say, oh, we'll propose this mechanism. This mechanism is plausible. This mechanism could be the one that shows us what's going on in this reaction. We cannot just use rate data to determine if the mechanism is true. We have to do other experiments. Um, so if we can detect the presence of an intermediate, then we can go, well, that's probably a good mechanism because we actually do see that that is present, right? If an intermediate is actually, we show that that intermediate exists at some point and then goes away, then that would make it make sense for that mechanism. So for example, in the hydrogen peroxide one, which was back here, if we could say, if we could find the presence of this, then that would support that this is a mechanism that could happen, right? I'd say, oh, hey, I know I see IO minus produced and then I see it go away, then that would be evidence toward that mechanism being plausible. That's just an example. Another example would be something like this. And so if we wanted to know, hey, if we have a reaction, which bond is going to break to make this happen? Would it be, so like this reaction here is used, there's water is going in and it's breaking apart this molecule. Is it going to break here? Is it going to break here? And then the water is HOH and it's getting used to kind of fill in the gaps here. So is this the H from water and the OH from water, or is this the OH, or is this the OH from water and the H from water? And that can kind of, so we're asking this question. So basically what we need to know is it breaking here, is it breaking here? So we can use a different mass of oxygen, a heavy oxygen. So oxygen usually has a mass of 16. We could use an oxygen isotope, oxygen 18, to flag it. And basically what we can do is use spectroscopy to figure out where that oxygen went. So if we essentially we're flagging this oxygen, um, when we used it doesn't gives us thing part of the story is missing. So essentially they flagged the oxygen in water. So they flagged this oxygen. They said, all right, the water oxygen is going to be oxygen 18. So where does that O go? Is it going to be this is the O with water or this is the O of water? And so water breaks apart just so we can have an idea of what's happening here. HOH. And what they did was they flagged this oxygen to make it heavy oxygen. Where does it go? So the two options are getting too far into this, so really don't need to know. That this OH became this OH, or that this OH became this OH. Like we're looking at which one is the OH from water, because the other would be the H from water. And so what we found was, or what they found was that the water, the O here, showing the OH, which means that this is the bond that was broken. So the OH, so this OH here essentially came in and plugged this bond's hole here. And then this H here went on to make the CH3OH. I can show you in class a little bit more if you're interested. I don't think it'll be something that is incredibly like important for you to know, but just know that we do have to do other experiments to figure this out. This will make more sense when you get into organic chemistry. And the last little bit we're going to talk about in this chapter is catalysis. I've talked about it before, but we didn't really sit down and define it. A catalyst is a substance that increases the rate of a reaction and is not consumed. And so the catalyst is something that is a reactant and then used later as a product. It speeds up a reaction by providing another set of elementary set of steps that have easier activation energies. They have lower activation energies. So a catalyst might take a reaction that looks like this with a high activation energy, and it just lowers the activation energy. It makes that transition state more stable. So it goes faster, because if you think about having to walk up this mountain versus this mountain, the shorter one is going to be faster. It doesn't change where we start and where we end. So I want that to be noted, is that it's not changing the overall reaction at all. It is just coming in and then it's leaving. With two types of catalysts, homogeneous and heterogeneous. Homogeneous or heterogeneous is the reactant and the catalyst are in different phases. And so your catalytic converter in a car is a heterogeneous catalyst. It's a platinum catalyst. And basically it collects the nitrogen monoxide and it gives it a place to form nitrogen and oxygen. It takes in carbon monoxide and oxygen and gives it a place to form carbon dioxide. And so these are gases, and then the catalyst is a solid, usually platinum. Platinum is involved in a lot of reactions, so I'm not sure exactly what this one is, but platinum is involved in a lot. Homogeneous catalysis, the reactants and catalysts are the same phase. So usually liquids can be gases, but same thing. This reaction has a rate that's dependent on this acid or this compound. And then if you add an acid to it, the rate now includes the catalyst, but it goes a lot faster when you have an acid. Homogeneous catalysts, advantages, you don't have to worry about the two different phases. And generally cheaper, because it's a lot of times the solid catalysts that we use are metals like platinum that are not inexpensive. And then lastly, you're familiar with biological catalysts if you have heard of enzymes. Basically, that's the same kind of thing. It just gets the right orientation. So the enzyme brings the substrate together. You make the enzyme substrate complex, and then the enzyme, it allows the substrate to do its thing to make your products. Or sometimes it brings two substrates together to make them make a product. Notice how the enzyme seems to fit the substrate. So enzymes are proteins that are folded in specific ways to fit their substrate. If for some reason the protein folding doesn't work correctly, then you have some sort of genetic mutation that keeps the enzyme protein from folding correctly, then you would have something that wouldn't work as an enzyme. And we do the same thing with thinking about catalyzed enzyme, but enzyme kinetics is a little more complex. But essentially, you could think about the enzyme substrate complex as an intermediate. And so you have enzyme and substrate, enzyme and product. And notice that the enzyme is in, and an enzyme comes out again. And then you can see here that it is a little bit more complicated than what we're used to, but it is still easier to do this in 2 steps than it is to do this one. I don't think you'll need this equation, but just in case any of the I don't think it's on your student learning objectives for this chapter. But the rate is always dependent on the enzyme substrate complex. All right, that's the end of chapter 14, and we'll see you in class.